I think we can all leave here learning something. So that's what I hope, is that I give you some nugget that you can take back that will impact the work that we all do every day. So I do want to just give a little background about why I am here, and I'm actually here because of a man named Roger Mackmeyer. Some of you may know his name. He wrote in the Pumper magazine for years. He started our program at the University of Minnesota in 1974. So longer than I've been alive, or around the same time. We've been doing education and research about septic systems, which is actually pretty remarkable. That led to doing homeowner education, and we also do research. And most of our research is very applied research. It's not like theoretical in the lab, brand new ideas. It's actually trying to solve problems in our industry. But I couldn't also help but mention a few things about Minnesota. I always say there's really one reason why people live in Minnesota. Do you guys know? Because you were born in Minnesota? No, I'm just kidding. Minnesota is a beautiful state, but we do have like 5 months of winter. And we had our first snowfall a couple days ago, which is very early for us. But you guys know our motto, we're the land of 10,000 lakes, is what's on our license plate. We actually have over 11,000 lakes, but 11,842 doesn't have an amazing ring to it, right? Lots of streams, rivers, wetlands. I don't know that we're fortunate enough to claim this one. The coldest temperature recorded in the lower 48, a town that's called Embarrass. I don't know how it got that name, right? No one can take the claim on Alaska, though, as far as being the coldest. There are things you probably use every day that you might recognize that come out of Minnesota. So Cheerios, 3M. Other things, famous people, right? My famous person right there, my favorite Minnesota famous person is Prince. My husband would be Dylan, who's up in that left corner. This movie makes all Minnesotans sound bad. If any of you have seen the movie Fargo, I would like to point out that Fargo is not in Minnesota. It's actually in North Dakota, and that's, yeah, sure, that's how they talk up there in the north. So, but my favorite part of Minnesota is actually the outdoors. The upper fifth of Minnesota is called the Boundary Waters Canoe Area, no motorized boats. It is a spectacular state all year round. And the cold does keep our population at bay, so maybe that's good that lots of people don't want to move there. So with that, I do want to get to the topic at hand, which was advanced systems. And when Sergio asked me to speak, we then had a conversation about, well, what are advanced systems here? Because across the US, it does vary. And what he told me is that you guys put in a lot of aerobic treatment units. So I'm not going to spend a lot of time talking about those because you already know, have a good understanding. So I wanted to talk about some other alternatives. But before I get into what are advanced or alternative systems, I also wanted to talk about, well, what are our conventional systems and why do we use those? Why are they so common? So when we think about conventional treatment, typically we're going to start with an anaerobic septic tank, which septic tanks are amazing. For what they cost and what they do, they take 50 to 70% of the solids that come out of a house and they generally settle it out and anaerobically digest it. So when you think about what that tank costs and what it does for treatment, it's really, really inexpensive. Unfortunately, those septic tanks don't do a good job at removing viruses and bacteria, primarily because it's anaerobic, which is very similar to our digestive system, so those bacteria and viruses make their way out of the tank. So in a conventional system, we use unsaturated soil to do that virus and bacterial removal. Probably the big downside of our conventional systems is that we're going to form over the long term, and I'm talking about 20, 30, 40 years, a clogging mat. That clogging mat in the beginning, the first 30 plus years, is actually our friend. It's microorganisms that are consuming the wastewater, breaking down the contaminants. But when systems do eventually fail, it's not just bacteria. It could be things like lint, right? It could be anything that's going to plug up the soil pores. But eventually that will need to be replaced. And then I think another big advantage of our conventional systems is that they're very low maintenance, right? When you have a gravity flow system, if you're lucky enough to have the site and soil conditions, now we're looking at needing to really maintain our septic tank, which is a very passive treatment component. So these aerobic conditions are what most of our systems are designed to have, and that means that our pores in our soil are filled with air, which has oxygen. When that is the condition, the microorganisms are naturally going to be there. It is important that as installers, for those of you who are serving that role in the room, that we protect that soil. And that means that during the construction process, the soils are not smeared or compacted. And we're always shooting to have soil that is not saturated, certainly when we put the system in, but when we start putting all this water out to the drain field, it's important that it's going to stay unsaturated as well. So to me, these aerobic organisms that live in the soil, that live in ATUs and media filters are pretty amazing. They take, again, our dirty wastewater and they remove a vast majority of the contaminants in a relatively small footprint. This anaerobic process is 10 to 20 times faster than the anaerobic process in a septic tank. And these microorganisms are very effective at converting the organic matter into various gases into cell tissue, right? They're making more friends, they're reproducing. They also start the process of breaking other nutrients out of organic compounds. These microbes do have some requirements. The first one you'll see is that temperature must be life-sustaining. I did expect when I came here it was going to be warmer than Minnesota, and it wasn't. But generally speaking, you probably have less of an issue, but once really the ground gets frozen, right, the microorganisms really slow down. They don't like to be cold either. The second thing the microorganisms need is a steady supply of food. They're like you and me, that if you stop the system, if no wastewater is going out to whatever treatment system you have, the microorganisms are going to eat what's around, what's left over. They might eat each other. And after that, if the food source is gone, what's going to happen? They're going to die, right? They need a steady supply of food to maintain a stable microbial population. One benefit of the soil is that if you are putting, and you have some generally a thicker topsoil layer, for instance, that black that we see in topsoil is food, it's carbon. So that can actually serve as a food source. The microbes in our system do prefer a relatively neutral pH, so we want to avoid things that are really acidic or basic. And we also do need to be careful of biocides, anything that is designed to kill bacteria, right? Antibacterial hand soaps would be an example, antibiotics. Very harsh cleaners and chemicals all can negatively, in large amounts. One pump of the liquid hand soap isn't going to kill off all the microorganisms. But let's say instead you're working with a restaurant that uses a lot of quaternary ammonia, which is an incredibly strong disinfectant. It could negatively impact the bacterial community in the system. So looking at a soil profile, and this may or may not represent your exact soil profile on the next site you're at, but it does hold true that if you take a gram, a small handful of soil from the top of the soil profile, you will find in the range of 1 billion bacteria, fungi living in that soil. That's why I always think it's hilarious when people are like, you need to seed your system, you need to put bacteria into it. There's bacteria everywhere. It's on your skin, it's on this table, right? And it's in the soil, natural soil microorganisms. But I do also want to point out, and again, if you just think about, you may not have exactly this topsoil depth, this A horizon going to this B horizon, but what will notice that as you get deeper in the soil, there's going to be less microorganisms, right? We're going from 1 billion at the surface to 100, which is a huge decrease. So again, if we're going to put in conventional systems, the higher we put them in the soil profile, the more natural microorganisms will be there for 2 reasons, right? One is the black, which is the food source. The second thing is oxygen supply, which is what they want. But what if you don't have all this good soil, right? What if you can't do a conventional system? So there could be many reasons. It could be that you have a high water table. We deal with that a lot, being the land of 10,000 lakes. Could be that you have poor natural soil conditions. So this could be a situation where you have very shallow bedrock. Could be that you have permeability problems. Usually we think about it on the high end, right? You have really heavy clay and you can't get the water in. But also if you have really gravelly sand, that's not going to be great for treatment either. The water will go away, but it may not be treated. There's also properties, and we see this a lot, existing properties, or sometimes some of those new lots we're developing, we developed all the easy lots, right? So now we're left with areas that have been filled, compacted, altered. Or it may be existing properties where they really weren't sustainably sized lots and now you don't have a lot of soil to work with. So then why might you use an advanced system? And I think this first one is often one that's overlooked, but it's to extend the longevity of our existing soil treatment systems, whether that be one you're putting in today or one that's been in the ground for 20 years. When we have a soil treatment system, it is doing, I mentioned, all the virus, conventional, all the virus and bacteria removal, and still a fair removal of organic material. If we pre-treat the effluent before the soil, we could extend that soil treatment system much past the 30 or 40 years. There's also people who are always coming up with a new and better widget, right? A new way to treat wastewater. But more commonly, it may be because you have sizing restraints, you need additional pre-treatment before the soil, you may have separation issues where you don't have the required separation to your limiting condition. And then there's all those siting problems where you have difficult soils or you have a really pristine environment where you need additional treatment to make sure you're protecting the environment. Nitrogen is probably the biggest contaminant that's getting a lot more attention across the US. Nitrogen in particular is really, can be really devastating to ocean environments. I probably live as far away from one of those as you can. We're really concerned about phosphorus. That's what makes our waters green. But we're also seeing issues of nitrate contamination in groundwater. So, and we're not the only source, but we are a potential contributor of nitrogen to the water tables. So why not? Well, the increased cost would depend. So we don't do surface discharging systems in Minnesota, but I understand you all do here. And when we're looking at doing pretreatment, we still have to have a soil component. So for many states, it adds additional cost. But I think it is also fair to say that there is usually, and again, it kind of depends on your soil treatment system, there's additional maintenance. And also because of, particularly if you're off-lot discharging, there needs to be more regulatory oversight to make sure that we're not just talking about pumping a tank every 3 to 5 years. We're now talking about maintaining systems every 6 months or annually, sometimes even pulling samples. So when we look at advanced treatment units, they have some common goals. And the first and foremost is to remove the oxygen demand. And not 100% of it, but usually 95% of it can be removed. So this is the BOD measurement, right? How much oxygen is needed to break down the organic material. The second one is removal of suspended solids. So that's what makes water look cloudy or turbid. So coming out of an advanced treatment system, we're hoping to see effluent still not safe to drink, but that actually at that point looks more like water. So now we could possibly do some disinfection, or we could put that to a smaller soil treatment system. Particularly vertical separation and square footage. So what happens during this process is, and this is regardless of the type of secondary treatment system, those organic compounds are going to provide food and energy to microorganisms. The naturally occurring microorganisms are going to consume the food and create more microorganisms. The more microorganisms, the more food's consumed. The more food consumed, though, the more oxygen. So we're trying to keep these all at a balance of how much organic material, how much bacteria, how much oxygen. So the true benefits are, you can see reducing organic matter, pathogens, and sometimes nutrients, depending upon the design of the system. So the effluent that comes out of an advanced treatment system will have a reduced biomat in a soil absorption system. You're still very likely going to form a thin film of microorganisms because there's still going to be some food and nutrients present in the water. The secondary treated quality effluent now is going to be able to easily go through a tertiary step. So that could be disinfection or nitrogen removal. This effluent now, we're talking about it looking like water. So it can be applied to a wider range of soils because we're now not asking it to treat wastewater, we're actually asking the soil to disperse water back into the environment. And therefore you see it can be done at higher loading rates. So most codes in the US allow for a higher application of secondary treated effluent and often in other soil conditions that otherwise you might have been limited to. So the pretreatment systems I'm going to focus on today, the pretreatment prior to the soil, or in your case maybe to discharge. The two most common are forms of media filters and aerobic treatment units. These units may be coupled with disinfection depending upon where you're discharging to. They may also have recirculation. So recirculation is common when your goal is nitrogen removal. The other alternative I'm going to talk about is importing soil. So if you don't naturally have the soil on site, you could bring it in by bringing in clean sand, which is commonly referred to as a mound system. I sometimes hear them being referred to as Wisconsin mounds, which is almost fighting words in Minnesota, right? It's like, so it was interesting. Mound systems were really developed in the upper Midwest, Minnesota and Wisconsin around the same time. We do a lot of them. So we use a lot of passive soil treatment versus mechanical. So why would you need higher quality effluent? Well, again, it could be because of an environmentally sensitive area. It could be soils that won't accept septic tank effluent, or where your land area is small. Another application is when you're looking into more commercial or cluster systems. When you have a lot more flow, you may be able to mitigate some of that flow by having, again, cleaner effluent. So this can lessen the impact of the dispersal system because you're allowed higher application rates, and again, where you may want to use spray irrigation. So media filters are designed to follow septic tanks, and the key reason is we are using media which is similar to soil, so we want to remove a lot of those solids so they don't plug up the media filter. It is a fixed film treatment system, meaning again, the effluent as it travels over the media filter is going to come directly in contact with whatever that media is. So the big difference between this and an aerobic treatment unit is that it's passive aeration. We don't have a blower, a compressor. We're just taking the natural air around us and allowing that to dissolve into the treatment system. So there are different ways media filters can look, right? The last picture I showed a container containing media. It was more common in the past that you would actually dig an excavation, and these sand filter type systems are still used. So again, what a media filter is either a container or a lined excavation with a very specific media with wastewater flows. So again, an aerobic fixed film bioreactor, and the treatment occurs in an unsaturated flow, meaning we're going to apply a dose to the top of the filter and it is going to slowly trickle through that media filter. So there are different types of media filters, and the real question is how many times is the effluent passing through the filter? So with single pass filters, again, the effluent's going to go through only once. Like you see here in the picture, it's collected in a bottom drain. That bottom drain can then either go out to a soil dispersal system, or it actually could, again, in some applications, be surface discharged. The second type of filter are ones that are designed to recirculate, meaning the effluent is going to go through that media filter many times, and it really depends on the technology how many times before it then goes out to a drain field or discharge. So showing a layout, so you can see here I have a 2-compartment septic tank. Very commonly there'll be an effluent screen on the way out to further limit the amount of solids. So in this case, you can see there's a dosing chamber that's dosing the top of an intermittent sand filter, then again going out to a pressurized drain field, which again is just going to optimize that final tertiary treatment in the soil. So if instead you have a recirculating system, and again, the primary goal of these recirculating systems is to remove nitrogen, we're actually going to take the effluent that's gone through the recirc filter and take it back to a recirc tank. And in that tank, you can actually see the nitrate nitrogen be denitrified if the right conditions exist. So why do recirculating systems have increased nitrogen removal? Well, the key thing is as the ammonia travels through the media filter, it is rapidly converted to nitrate. That process happens really well. So what you will see is that ammonia process always happens in our conventional systems, but the problem is nitrate continues to travel unless there's a denitrification process. So that process can happen in that recirculation tank. So again, other benefits of why you might think about a single pass over a recirc is the filter, the top of that media filter is going to receive a diluted effluent. And what I mean by that is it's going to be in that recirc tank, it's a mix of effluent that's come from the septic tank and effluent that's already gone through the filter. So now the amount of organic material that's present is decreased, so you can actually apply a higher loading rate. And the real benefit of that is a smaller filter, right? So now you're not talking about something that's 400 square feet. That could be a small box. So the smaller filter surface area needed for the given flow, it can withstand somewhat higher waste strength. So we see some of these commonly put on like a convenience store where you have a lot of toilet flushing. So it's not like a restaurant where you have really high organics, but elevated BOD and TSS levels. Another benefit of these systems is they can cope with flow variations. Because of that recirculation nature, if you have high peaks or low events, it kind of helps dissipate some of that loading. So one of the benefits of moving away from sand filters, which were these lined excavation, is modular units. So these are now filters that are proprietary by nature that come in a box. And from an installation standpoint, they're much similar to aerobic units, right? That you basically make 2 wet connections, you hook up your electrical components, and you can be good to go. So lots of different types of media. Historically, wash-graded sand and gravel were the most common, but we've definitely moved towards more manufactured media. And I think there's several reasons for that. One of them really is quality control, that finding the right kind of sand, the right kind of gravel in some parts of the country can be very difficult. So you'll see foam chips and cubes, peat, and we've probably all seen coconut milk now at the grocery store. Well, there's a huge excess of coconut husks, right? And so a company actually, instead of using peat, which has to be farmed and takes a long time, has developed a robust system that now uses coconut husks as the treatment media. Synthetic textile media, crushed glass, and there'll be something new. People are always coming out with often repurposed, and if you think about it, that's what the peat and the husks are, but also new ideas, new innovations around the type of media. And I think this picture might show well, so this is a foam cube, very high surface area, and if you think about a foam cube, when you apply water to a foam cube, what happens, right? It actually hangs on to it. You get really good retention time and very high surface area. A lot of this media is also designed to have lots of locations for the bacteria within the filter to hang out, and that's what bacteria likes. So in media filters and in mound systems, the wastewater is applied in small doses to the top of the filter. We have that thin film of wastewater traveling. The organisms are actually sitting on the media, just waiting for the wastewater for the food to come by. And we don't apply too big a dose because we want to make sure that there's still air present in those pores. The oxygen is actually transferred from the pores into the thin film to the organisms. And 99% of the time, the aeration is passive. I've seen a few examples where they'll actually put drip tubing into a filter and actually pump air in. And they're usually doing that because they want a really small footprint, that they're looking to maximize oxygen transfer. So slow, unsaturated flow provides sufficient retention time. And that's one of the biggest advantages of septic systems over municipal systems, is our effluent spends so much time getting treated. It's not a one-day process in and out, right? We're talking about days of treatment between our septic tank, our pretreatment systems, and then the soil. Most media filters, and not all, but generally speaking, are also time dose, which means the pump that's in the system that's doing that even dispersal is on a timer. That helps the microorganisms in the system perform better because they're fed on a more regular basis. So the treatment occurring, and this is true of all soil components, whether it be mounds and media filters or conventional systems, from day one they are working particularly through this first process, which is a physical treatment process of filtering and trapping contaminants. There's also chemical processes going on where different contaminants are absorbing onto the soil interface. We've commonly looked at phosphorus, right? Phosphorus will absorb onto the soil, but we're seeing more research about chemicals of emerging concern, things like ibuprofen and antibiotics also being retained in the soil. What's even better than just absorbing is actually breaking down. So that's the third process, would be a biological degradation or decomposition of the contaminants in our wastewater. So here again shows startup of a sand filter. So again, this is a pressure application where you can see all the orifices are squirting up, and they're squirting up pretty high, right? That looks like 5 to 10 feet. So they had a pretty decent sized pump on that system. So what about the effluent? What kind of quality can we expect? So you'll see the column in the middle shows what the general range we expect to see coming out of a septic tank. So a septic tank and a media filter are all pre-treatment. They're all pre-treating it before either the soil, or if you're going with something as clean as a media filter, an ATU may be discharged. But what you'll notice is, right, you're looking at a BOD around 200 moving down, and when you look at a media filter, it'll be less than 25. That 25-30 for BOD and TSS is again below a discharge standard. The total nitrogen, again, the levels you'll expect will depend if it's a single pass or a recirc. A little phosphorus removal, but not, again, all the way down to 0, which we'd like to see at around 1 if we're actually going to be discharging. And then you'll see the fecal coliform numbers. So that's the indicator of bacteria and virus removal. Again, generally, media filters are going to be doing a pretty decent job. You see anywhere from 100 to 10,000 microorganisms in the effluent. So just some pictures to show you different examples. So here is one of those foam systems. It actually is the only one I'm aware of that uses a helical nozzle to spray across the top of the system there. Here's a textile filter, and you can kind of see in our hands, it's a sheet of textile that the effluent travels over. And again, the footprint of this can be very small in someone's backyard. Examples showing the cocoa and peat filters. Again, there's two primary companies I see selling this. Some use Irish peat, some use Canadian. But I mentioned the Canadian company is actually moved towards using a cocoa husk versus peat. The thing to keep in mind with peat, and cocoa, is that over time they will degrade, right? They're an organic matter, so they do need to be replaced. But the typical, and again, how often you need to replace the peat is just like me asking how often you need to change the oil on your car, right? Depends on how many miles. But you're generally looking at, 8 to 15 years. Like, it's not a regular occurrence, and it really goes back to use. So these systems, again, can be designed to either collect the effluent or in some applications can actually drain out the bottom, but you have to have the right soil conditions underneath them to do that. So as far as access, I think that's one of the other big advantages. I've shown you a lot of containers where you can see and access the media. With sand filters and recirc filters in the past, we'd have to dig them up, right, to get at them, where now we have a lid where we can actually open them up. So they can be buried or free access. The free access filters often use gravel or foam or textile or peat. The containers, again, typically you're going to have covers. Those covers certainly protect them primarily for access and the elements. They are generally going to be below the ground. The ground particularly helps insulate them when we do get colder weather. The microorganisms in the systems, again, in general, prefer to be warmer. They're going to consume more food when they're warm. So kind of thinking about this as we wrap up the discussion about media filters is I just wanted to compare this. The treatment that you will see coming out of an ATU is similar to the effluent coming out of a media filter. The big difference is ATUs are saturated, right? They're a tank full of water, and we're trying to, again, get that oxygen into solution. So we're going to have water and solids, and the actual air-water interface is minimal in comparison to media filters. And it's a mechanical process, right, that we are using a blower, a compressor, an aspirator, one way or another to get those bubbles into the effluent and hopefully into solution. Media filters, again, are not saturated, so we're going to have air, water, and solids. We're going to, as much as possible, maximize that air-water interface by using passive aeration. So with that, I did want to just discuss what is passive aeration. So this is, again, what we use in our conventional systems, but also what we use in media filters and mounds. And this is an example, and this, again, wasn't done for septic system. It was actually done for agriculture, where they were actually looking at what's the oxygen levels in the soil. So they went out during a wet time of the year when they were getting a lot of rainfall and compared it to a dry time. And this was not saturated soil. And what you'll see is they measured at 4 inches and then they went down almost to 48 inches. And they measured what is the percent of oxygen. And the air around us is 21%. That's what we're all breathing. So you'll see during the dry time periods of the year, 4 inches below the ground, it was almost at 21%. If you went all the way to 4 feet in the ground, it went to 16, which isn't a huge reduction, right? But it is less as you go deeper because it's passive. It's just kind of working its way down. But I thought what was probably even more interesting than that is how does the oxygen level change when you're during the wet time of the year? When you get a couple inches of rain, right? Some of that water is going into your soil pores. And even though it's not saturated, there is less pore space available. So you can see that it started at 14, 4 inches below the surface, and went as low as 8% oxygen. So this is the natural oxygen we're using in media filters, in mounds, and in our conventional systems. So with that, we are going to move into discussing mounds, and all mounds are an elevated, basically pressure bed or elevated trenches that you have a vertical separation requirement. You can't meet it with your natural soil conditions, or the natural soil would have trouble accepting septic tank effluent. So we're going to import sand to do it. So when we look at sizing mounds, though, we're going to build the sand bed, but we have to keep in mind what is the underlying soil underneath the sand. And I've been to states where they're like, no, our soils are so tough you can't make anything work. So we have soils in Minnesota that perk at over 120 minutes per inch, and we put mounds on them. They're not small, which means they're not inexpensive, but we don't have the option of discharging. And Sergio told me you guys do some spray irrigation here. If we sprayed in the middle of winter, we would have sewage ice skating rinks, right? Like, it just doesn't work in our climate. So this actual size of the mound is based upon, sure, we're going to build the sand bed, but how big and wide it needs to be is based upon the underlying soil. So the media, the natural soil, the waste strength. So a clay soil is going to have a bigger absorption width than if you had sand below it. And you'd be like, well, why would you build a mound? Why would you bring in sand on a site that's sand? Well, you may only have 18 inches to a water table. So we have to bring in additional soil to meet our separation. So again, what a mound might look at laid out on the property, you'll see kind of across the middle is the media / rock bed. And then the downslope area is actually that absorption width. So the effluent's going to travel through the sand. And actually the BOD and TSS is removed in the upper 6 inches. The reason why we have separations beyond 6 inches isn't for removal of organics, it's removal of bacteria and viruses. So it's going to travel through the sand, but it's going to hit, and let's say in this case it's going to hit an underlying clay loam. The clay loam isn't going to take the rate at the same as the sand, right? Things are going to move quicker, so we actually have to size it based on that downslope required width. So how we decide how big and long the system is also based on a term called the contour loading rate. This is, again, how much water we expect to move down versus sideways. And we all know this, even though I've had homeowners think, well, it all evaporates, right? All the wastewater from their septic system, which even in the driest part of your state, I don't think that's reasonable. I think we have to expect, if you have a soil dispersal system, that some of that effluent is going to move down, and it might not move all straight down, that some of it's going to need to move laterally. So we pick a contour loading rate based on those soil principles. So a mound, again, is typically going to have 1 to 2 feet of clean sand, and the word clean is very important. When we first started building mounds in the 80s, we used often what people referred to as pit run. It was dirty sand, had lots of silt and clay mixed in, and those mounds didn't last. So a very specific sand. We're going to have a septic tank, a pump tank, and pressure distribution. So we're going to evenly apply the effluent across the soil. And that is another, I know homeowners think pumps are 4-letter words, right? But a pump in a system is the best way to achieve good treatment. Because when we look at our loading rates and all the research that was done in the 70s, it was all done based on an even application of effluent to the soil. So again, most people have wells, right? And they have a well pump. So, and they last a long time, so do septic pumps. So then we're going to have a distribution media, and I'll show some examples. We used to use historically a lot of rock, but many installers have moved towards using other distribution media besides rock. We typically build that bed, whatever it be filled with rock, chambers, easy flow, you name it, 10 feet wide, but I go across the state line into Wisconsin, and they build a lot of 5 and 7 foot wide beds. We place sand in the absorption width, and then we actually extend soil to either a 3 to 1 or a 4 to 1. You can go 5 to 1. It'll blend in better. It'll look less like a hump in the yard. But as you start bringing in more material, the cost of the system goes up. So looking at laid out on a property, right, we see in this case they're lucky enough to go gravity to their septic tank, gravity to their lift station. The lift station then doses the mound system. So kind of looking at it from a side view, this one shows it as one bed across the top. It could actually be installed in this case, as you see, as kind of 2 trenches sitting across the top of that sand. You do have to have some unsaturated soil, right? So sitting underneath that sand bed, we designed to have at least a foot of soil. We have sites where we have bedrock where we might not have a foot, and then we just bring in more sand. So how it again looks like, our topsoil, which we actually leave the topsoil in place on some of your more limited sites, it's the only good soil you have, right? So we scarify that surface, we put down the required amount of sand, we bring in our distribution system with our pressure pipe, geotextile if you're using rock or easy flow, and then cover, which you're going to get something to grow across the top of there to particularly prevent erosion and certainly frost from going into the system. So here again shows a mound being built with the easy flow product. And when I first saw this, right, I thought it looks like packing peanuts, right? Well, do you know what happens if you put a packing peanut in your mouth? It dissolves, which is a fun party trick, right? But this is different. This is very different, right? It doesn't dissolve when it gets wet. And it's also very strong, right? You can drive across the top of that. But this again shows where they're putting a pipe basically in every 3rd lateral to disperse across the top. Can be done with chamber systems as well. So we used to just build them with rock, but we found that for various reasons, I mentioned clean rock is hard to get in some parts of the country. So using other media, the purpose of distribution media is to spread the wastewater out. The magic happens in the soil. So management and maintenance is essential. So with these systems, media filters and mounds on an annual basis is what's typically going to be required. It needs to be done by one of you all, right? Someone who knows what they're doing. Some counties and states will have a tracking system to ensure systems are being maintained, and we are certainly moving in this direction, that more systems and more regulatory authorities are tracking. Because when you think about the comparison between wastewater treatment plants, that's one of the big differences, right? They have operators, they have reporting. Well, we've seen particularly in certainly our more populated counties that that's the direction we're moving, is that when people get their tank pumped or have their ATU serviced, that they're actually required to report that information. So we know that, again, we're protecting public health and the environment, which is why we all have jobs, right? That's what septic systems are doing, is they're taking dirty water that's full of contaminants that make people sick, can harm the environment. So having, and I think there's pros and cons, because certainly it takes a lot of work, right, to track and know what's going on. But if we don't have that, do we actually know that public health is being protected? So what's typically involved with maintenance? Well, if we have pressure distribution, those laterals over time will have both water and sewage and nutrients, so we'll grow some slime, we might collect some solids. So flushing those laterals, and again, that might be every 3 to 10 years. We're not talking about something that typically needs to be done annually, unless you're looking at more commercial strength waste. With some of the media filters, you may need to rake the media, and this is particularly true of peat and the coconut husk ones, because you can get some uneven settling as things are degrading. You may need to replace media over time, clean, and then the most critical one is what's true of all of our systems, is making sure that your tanks don't have too much sludge in them, and then certainly cleaning effluent screens if those are part of the system. So aerobic treatment can help solve problems. I firmly believe that. There's lots of different ways to do that, to get at aerobic treatment. So it could be a solution if you don't have enough separation or if the soil is coarse. So the effluent that comes out of the systems we've discussed and ATUs is going to have fewer pathogens, right? We're going to have killed off a lot of those bacteria and viruses because they don't like oxygen-rich environments, right? They were used to living in our guts, which are not full of oxygen. If your site is too small And the real advantage here is we are going to take out most of the BOD and TSS, so now we can have a smaller footprint. If your waste strength is high, and I really didn't get into this in this talk, later I'll talk more about organic loading, but when you start getting into anything other than residential homes, when you start getting into commercial flows, to me, pre-aeration before the soil is almost required. The loading rates that you have in your code, that we all have in our codes, assume domestic strength wastewater. So now if you have, and let's just say it's a convenience store, not even doing a lot of cooking, lots of toilet flushing, little bit of food debris, maybe they have one of those soda fountains, they're awful, right? The BOD coming out of a soda fountain, even a little bit of it will impact your wastewater stream. So if you have one of those, and let's say the BOD is coming out as 500, when you put that out to a conventional system that wasn't designed for it, or even a media filter or ATU that wasn't designed for it, there's not going to be enough oxygen to deal with that high amount of organic material. If you have a system that is near or failing, this one sometimes gets a little hard, but there was a study done in Wisconsin where they actually went out to over 20 systems that were hydraulically failing. They were otherwise good systems, but they determined that they were biologically clogged, and they added pretreatment. So they were conventional soil dispersal systems. And in their research, 3/4 of them were recovered, but 25% weren't, right? So that's the risk if you have, and I'm sure you've gotten this call maybe from a homeowner that says, I was on the internet, right, and I saw if I put in this, my favorite one is, right, I put a product in, it'll magically solve my problems. Or I put in a spinning blade, that's going to fix my problems. And the answer is, well, those are probably two bad examples, but there could be. It could be that if you sent cleaner effluent out there that had some residual oxygen, that you could recover some of the soil properties, but not all of them, right? Not everything that we put out to the soil is organic and biologically able to be broken down. Also, if nitrogen is a problem, so this is out on the East Coast, I was just in Virginia, they have to put nitrogen removal on every system that is ultimately ending up in the Chesapeake Bay. So there's a huge amount of growth in the area of nitrogen removal related to pretreatment systems. So with that, this is my email and website. So if you have questions, I'm going to be here all day and I'd be happy to chat with you. But also, if you ever say, you know, I really want to put in one of those mounds, our entire manual we use for all our training courses is online. We have lots of information out there for homeowners on a range of topics. And also, I'm happy to answer emails too. So 5 years from now, when you have that project that you want to talk about, feel free to reach out to me. Because I think to answer this question, I need to lay the ballpark of what an ATU costs here, right? Or versus because again, I mentioned all of our ATs are still going to have a soil dispersal component. So I think what I heard is that the range of what an ATU may cost here, and you can tell me if I was right, because I think you told me maybe around $7,500? So 5 to 10, we're going to throw it out there, because it probably depends on your house, the type of system you put in. Do you put a septic tank, a trash trap in front of it, which I hope the answer is yes. So then what does a typical mound system cost? And again, this all goes back to bedrooms too, and where in the city or in Minnesota you are? Outstate Minnesota, I'd say 12,000, as high as 15. I've seen ones cost 30. That has to be in very extenuating circumstances, but you know, that's how giving a price is always risky. So I would say about 15,000 is about the average cost, and it's certainly gone up in the last, I feel like 5 years. Everything's getting more expensive, so. Ultimately, our regulations don't allow homeowners to spray, so it would take a huge regulatory shift. That aside, I think the problem is now you're having someone kind of pay for two systems, and most people aren't interested. Like, so there's been more talk about wastewater reuse. Like, can you take, let's say, your shower water and use it to flush your toilets? The answer is probably, but you still have to have a septic system. So like it doesn't, you know, so to some people, you may find the homeowner who's interested in that, and it would do just what you said. It would lengthen the life of your soil dispersal system. So resting and alternating, building in that ability does provide additional longevity to your system. So you could. No. Because so I want my septic tank to settle out things. I do. The primary treatment that happens in a septic tank is settling. And if I put a way to introduce air and movement into that, I won't have settling. If you told me you had a 2-compartment septic tank and could I do it in the second one, capture most of my solids in the first. But a lot of those treatment systems I've seen that get dropped directly into the septic tank itself make a poor septic tank and to me a poor aerobic system. Because aerobic systems have generally, I would say, 3 things, right? They have a small trash trap, they have an aeration zone, and they have a clarifier. And I also want a clarifier somewhere for things to settle out that were in solution. So to me, I don't want to put one right in the septic tank because I want my septic tank to do its job.